Alright, so we were talking about interrupts on Thursday, and I made an impromptu list of things to know about interrupts, things to consider. So the first is different sources of interrupts. On the PIC processor, we have 3 pins we can use to generate an interrupt. They're called int0, int1, int2, and they're all located on port B, but not necessarily where you'd think. So int0 is RB0, int1 is RB1, int2 is RB2. But pin-wise, it's pin 8, pin 9, and pin 17. Okay, so if you're actually working with a chip, these pins are not next to each other, even though they're the first 3 bits of port B. Right? This is these multi-purpose pins. This pin 8 could be bit 0 of digital port B. It could be bit 4, or the 4th analog input channel, or it could be used to generate interrupt 0. Alright, so we have 3 interrupt pins that can generate inputs. We have timers that can generate inputs. We can say when an analog to digital conversion is done, or when a character is received by the serial port transmit-send subsystem, generate an interrupt. We can say when any bit on port B changes value, generate an interrupt. We can say all kinds of different things that might generate interrupts, and for most of these we can say, should that interrupt be considered high priority or low priority? Okay. And for some of these sources of interrupts, there are specific settings. For example, when we say int0 can generate an interrupt, we can specify should it generate an interrupt when int0 goes to 5 volts or when int0 goes to 0 volts. So the rising or falling edge. Each interrupt can be individually enabled or disabled. By default, they're all disabled. But we can enable them. We can say I want interrupts from the pin int0, the pin int2, and timer 3. So we can specify enabling for each individual source, and we can also enable or disable interrupts globally. And we can do that separately for both high priority and low priority. So we can say disable all the low priority interrupts, enable all the high priority interrupts that have been enabled individually. Each interrupt has associated with it an interrupt flag, which is set when an interrupt is being requested. And requesting an interrupt does not mean an interrupt is going to occur. If I've disabled interrupts globally, int0 might be requesting an interrupt, but it's not going to interrupt the processor. Right? So these flags tell us who's asking for an interrupt, but it doesn't tell us if that interrupt is going to happen or not, because that depends on the state of these enable bits, whether the source is enabled and whether globally interrupts have been enabled for whatever priority level that source is. And all of that, as confusing as it can be, is really nicely spelled out in the data sheet if you don't mind looking at Engineering 250 style schematics. So if you come to chapter 9, there's a beautiful picture here. This picture succinctly tells you everything there is to know about interrupts on the PIC processor. But it's a bit of a challenge perhaps to read. So for example, here's the int0 interrupt flag. This line right here is a 1 when int0 is requesting an interrupt. And that gets ANDed with a signal called int0IE. That's the interrupt enable. That's the bit from a register that says, have I enabled interrupts from int0? Okay, these are coming out of file registers. So if you look at your full data sheet, here's this int0IE bit. It's bit 4 of this register called intcon. Here's int0if, the interrupt flag. That's bit 1 of the intcon register. So one register has these 8 different meanings to it. Those 2 bits, the int0if and the int0ie, go into an AND gate. The output of this AND gate is 1 if exactly the following condition is true. Interrupts have been enabled from int0, and int0 is requesting an interrupt. That goes through an OR gate. The output of the OR gate here says somebody who is allowed to interrupt is requesting an interrupt. Same thing for the A to D conversion, same thing for all of these other peripherals. Okay, these are all high priority interrupts. So 1 on this line means somebody's requesting an interrupt. And that'll go through an OR gate to here, and that goes into an AND gate. How does it come out of the AND gate? Well, we need to have global interrupt enables turned on. So we need to have interrupt priorities enabled. Okay, that's bit 7 of RCON. That'll generate a 1 out of here. So now we have a 1 here saying somebody is requesting an interrupt. And that comes out of here, so now we've got a 1. Right? And you can trace these signals through. All of this ultimately comes down to a signal right here. This line right here is saying somebody who is allowed to generate an interrupt has requested an interrupt. Could be int 0, int 1, int 2, could be a timer, and so on and so forth. And that gets ANDed with this global interrupt enable high bit. So if the source is enabled, if the source is requesting an interrupt, and if global interrupts are enabled, then you get a 1 coming out of this arrow right here. That's what actually says, hey, let's interrupt the CPU. And the same thing down here, if you have low priority interrupts, right, we'll generate a signal here. So all of this combines all of these different registers, all these different bits we're going to talk about, into basically a pair of signals. One that says generate a high priority interrupt, another that says generate a low priority interrupt. And then the question is, once an interrupt is generated, what does the microprocessor do? What is its response? And it's very simple. It makes a call to a magic location in the program memory. So a high priority interrupt jumps to location 8 in program memory. A low priority interrupt jumps to location 18 in program memory. And it does it with a call. So it saves the address of the instruction it was about to execute on the stack, and then it calls one of these addresses. And if at some point the code at these locations does a return statement, it will go back to where it was when it was interrupted, and life continues. So the lab actually spells this out in a fair amount of detail. And this is largely taken from the book. So here's the PIC processor. For the lab, we're only dealing with these 3 interrupt pins, int 0, 1, and 2. The high priority interrupt vector is at 8 hex in program memory. Okay, vector is just a fancy word for location. But we can verb it. We can say that the processor will vector to location 8. It means it makes a jump to location 8. Low priority interrupt vector is at location 18. Okay, that's the location that the PC will be set to after an interrupt has occurred. By default, the interrupt happens when the input pin goes from a 0 to a 1. But we can change that so it interrupts on the falling edge instead. Alright, here's the RCON register. You want to set bit 7 to a 1 to enable priority levels. And these registers are mostly telling us things that have happened. And this is where we're going to start making really good use of this bit set, bit clear business. So Archon looks like this. This most significant bit, bit 7 of Archon, is used to say, do you want to allow priority levels? And if you set this to a 1, it means have 2 levels of interrupts, high and low priority. Okay, we would like to set that to a 1. So what could we do? Well, we could take, a binary mask like this and move that into W and then move that into Archon. But that's assuming that we know it's okay to write zeros into all of these locations. For Archon, that's not a problem, but for a lot of these other registers, each bit is going to mean something possibly completely unrelated to anything we care about. But we don't necessarily just want to write zeros into there. Really, all we want to do is set this bit to be a 1. So the proper way would be to read this into W and then OR it with a bit mask to force this bit to be a 1 and write that back. And that's a pain. So we're going to use these bit set file register instructions. Bit set file register Archon, comma 7. That's all we need to do. That says go into this register, bit 7, set it. If we wanted to make it a 0, we could say bit clear file register Archon, comma 7. That would write a 0 into there. And so when you look at code dealing with interrupts or timers or A to D or anything else, you're going to see lots of bit sets, bit clears. So those are really good instructions to get comfortable with. By the way, I should make the comment up front here. Lab 3 was, and homework 3 to some degree, was really kind of, sort of the extreme point of the software side of the course. Okay, we're moving much more into the hardware aspects of the PIC processor and working with the PIC processor. Doesn't mean we don't write software. We're going to be doing a lot of coding, but the code is going to be relatively easy compared to, say, Lab 3's code. Okay, easy in terms of algorithms. The complexity will be keeping track of, this register I need to set this bit, and that register I need to set these 2 bits and clear these bits, right? So a lot of low-level minutia, but we're really dealing with working with the hardware. Okay, so we'll be backing off from the sort of heavier programming aspects for a bit. All right, INTCON, these 2 bits you want to set to 1 if you want to enable high and low priority interrupts. If we want to enable interrupts from int 0, we use int 0 IE, that's the interrupt enable. And if we want to know if int 0 is requesting an interrupt, we can check int 0 IF, so bit 1 of INTCON. int 1 and int 2 are enabled in the INTCON 3 register. Now we can check for interrupts from int 1 or int 2 by using the IF register, is also in INTCON 3. Int 0 is always high priority. Int 1 and 2 can be high or low. And we use the INTCON 3 register to control the priority of int 1 and int 2. These 2 bits in particular, bit 6 controls the priority level of int 1. If we set it to a 1, it's high priority, a 0 is low priority. We can also control whether we're interrupted on a rising or falling edge. That's these 3 bits in INTCON 2. If you set this bit to a 0, it interrupts on the falling edge. If you set it to a 1, it interrupts on the rising edge. Okay, this is not for the faint of heart. This is a lot of figuring out what you want to do and then just digging into your data sheet and writing down lots of notes. You're going to go through your data sheet a bunch before you actually start writing any code. because you want to figure out exactly what do I need to do. I need to set, priority levels. I need to enable high and low priorities, enable int 0, and set the edge to this and the priority of that. Figure out all that stuff that you want to accomplish before you start writing code. And then figure out which bits in which registers need to be set to what value before you start writing any code. So this is high level stuff, right? I'm going to need to set int 2 IP to a 1 and int 1 IP to a 0. Right? Write that out on paper, or type it up or something in a way that's totally clear to you what's going on. And then you can start writing code. And writing the code from that is pretty straightforward. If I want int 1 IP to be a 0, BCF int con 3 comma int 1 IP. Right? These labels, int 1 IP, int 2 IP, these are specified in that include file. So when I said bitset file rcon comma 7, I could have done this. Bitset file rcon comma IPEN. Rcon is hardwired to the address of that file register. IPEN is already hardwired to be a 7. This is a lot less error prone than that. And it's also portable. If I work on a different processor, this code will still assemble correctly. We're avoiding magic numbers as much as possible. Alright, we're not going to worry about these other registers for a while. Except for rcon, set IPEN to a 1 to enable priority levels. Alright, so you can read through all of this in Lab 4, but I've given you the punchlines mostly. So when an interrupt is enabled, and the source requests an interrupt, and global interrupts have been enabled, the processor jumps to a magic location. It jumps to either location 8 or 18. Alright, high priority goes to 8, low priority goes to 18. And it's done with a call, which means at the end of our interrupt code we want to do a return. But here's the other thing, when an interrupt occurs, interrupts are automatically disabled. Right? There's no call waiting, so if your phone rings and you answer the phone, it won't ring while you're talking on it. That interrupt has been disabled. So before you can go back to life the way it was before the interrupt occurred, you need to re-enable interrupts. The trick is, if you were to re-enable interrupts at the end of your interrupt routine and then say return, it's possible you get interrupted before you did the return. Right? You really need to do two things. You need to enable interrupts and then return back to where you were. So there's a special version of return called retfee. And it does two things. It enables interrupts and it returns. So at the end of your interrupt routine, you always want to use retfee instead of return. Okay, so that's mentioned in here. Return from interrupt instruction, retfee. Alright, interesting note here, do not use moveFF to modify interrupt registers if you could get interrupted. You can break the processor. So here's an example from the data sheet, right? Let's say you're executing code down here at location 126. This should be an MOVLW. You move a 23 into W, right? And let's say you're at location 128 and an interrupt occurs. Okay, so you're executing this add instruction and an interrupt happens. Okay, you won't get interrupted in the middle of the instruction. Now, interrupts can occur anytime, right? It takes a certain amount of time to execute an instruction, but if I'm going to put 5 volts on pin 8 of the PIC chip, I can do that at any time I want. And it's not always going to be at the beginning of an instruction. So it's going to happen partway through an instruction. On the PIC processor, the current instruction will finish before the interrupt happens. So this instruction at 128 executes. The program counter is now 12A. So it's about to do this clearF, but it acknowledges the interrupt. And that interrupt causes a call to location 8. When that call is made, the address of the next instruction, 12A, is pushed onto the stack. So 12A will go on the stack. We'll do a call to location 8. Interrupts will be disabled. We'll do whatever this code is supposed to do in location 8, 10, 12, and then at 14 it says retfee. That re-enables interrupts and then pops off what's on the top of the stack, which was 12A, jumps to that, so it goes down and it does the clear. So from the perspective of my program that was running, I executed 126, I executed 128, I executed 12A. It just turns out that in between these two instructions, some other stuff happened. I got interrupted, a bunch of code ran up here, and then I came back. When you're writing code that deals with interrupts, you have to be prepared to be interrupted any time. And this is tricky. So there's this notion of side effects. For example, up here, I changed the value of the W register. Down here I put a value into W and I did some other stuff, right? If I expect the value of the W register to be the same from here to here, anything that can cause an interrupt, right, might throw me to my interrupt code. I've got to make sure I don't disturb the value of the W register, or location 89 or 90 or anything else. Okay, this is probably the trickiest thing about writing interrupt code, the fact that you can get interrupted pretty much anywhere in your program. So you got to be really careful what you do in your interrupt code. Okay, we'll talk more about that later. Let's look at some code. So here's a sample main program. And there's a few things I'm going to correct in this program. And then we're going to throw this into MPLAB and play around with it. So, I can't copy and paste from a PDF very well, but I can from a PDF displayed in Chrome. So I'm going to grab this code like this. Alright, so let's make a new project. Someone has their microphone on, by the way. So let's make a lab 4. And I'm going to make a new file and I'll call it main, and I will paste our code. Alright, so here's the code straight out of the lab. And let's fix errors before we start changing it. So, that is not valid assembly language. Alright, so this is sample code, okay? This is code we can use to explore what's going on. I'm going to make a few changes to this. So what's happening in here? Let me see how much is explained in here, and then I'll talk you through it. Okay, it just says demonstrate. Alright, so this program basically, it will blink a light every 2 seconds. It'll turn it on, it'll turn it off. It's the same old delay code that we've had before. This inner loop delays for 1/10 of a second, and you do the whole loop however many times you put in D count. So this should toggle bit 0 of port A every 2 seconds. Okay, but while it's toggling, it's on, it's off, it's on, it's off, it's on, it's off. While it's toggling, right, which means mostly it's sitting in this loop, you can interrupt it. If you generate an int 0 interrupt, it should jump down to this location of code and toggle bit 1 of port A. And I'm going to change this and say if you hit a low priority interrupt, let's toggle bit 2 of port A. Okay, this is classic interrupt code. The main program is just sitting in this loop. It does these 3 things over and over and over again. Toggles bit 0 of port A, that's the bit toggle instruction. Waits for a little bit of time, goes back and does it again. So without knowing about interrupts, we would expect that this is all the program would ever do. Turn that light on, turn that light off, and just keep doing that over and over. But because we have interrupts enabled, even though our code is doing this exact thing, we can fire an interrupt and we can cause something else to happen. In this case, turning on or off either bit 1 or bit 2 of port A. So how does this work? The first thing to note is that the beginning of our program is always at location 0. We don't start writing our code there. Why not? Because our code is really long. We've got a bunch of setup to do. We've got some clears and some moves and some bit sets and bit clears and then our main loop. And if we started this at location 0, this would be 0, 2, 4, 6. This move LW, that one would be at location 8. And that's where the processor is going to go when an interrupt occurs. And when an interrupt occurs, it makes no sense to jump down here and put F8 into W and move that into tris A. This is setup code. So at location 0, what do? We go somewhere else. We say go to main. And at location 8, we're going to put in the code we want to run when a high priority interrupt occurs. Well, if we only have 16 bytes worth of instructions, we could put them at location 8. But a safer thing to do is at location 8, let's just say go to somewhere else. And now we know location 18 is still available, and we can say go to somewhere else there. So we're breaking up our code, right? We're setting it up so that here's the reset vector. Here's the high priority vector. Here's the low priority. Right, this is location 0, this is 8, this is 18. And then somewhere else in our program we're going to have main. And when we reset, we're going to jump down to main. And we're going to have a high priority. And when we get to our high priority vector, we're going to jump down to our high priority code. And we're going to have a low priority section of code. And when we vector to our low priority interrupt, we'll just jump down to low priority. So the only thing we're doing with these first few locations, say the first 32 locations, is we're just putting in a bunch of go-to statements. We're not actually writing a bunch of code up here. we're using those to jump to other locations that aren't special purpose, so that we can write as much code as we want. So 0 goes to main, 8 goes to H prio, 18 goes to L prio. And then we started location 20. So here's the main code, and it'll go down through a main loop. And then that's followed by our delay code, and that's followed by our high priority code, and that's followed by our low priority code. Let's see, so question, does this stuff get executed in random access memory, so like another program can also use location 0, for example? So on the PIC processor, there's just physical memory, there's no virtual memory. File register 0 is always file register 0. We don't usually have multiple processes, but any program that we load in, right, can use file register 0. Or location 0. But yeah, it's really kind of one program per chip. It's random access memory in that you can read and write from any location that you like. But this is, the physical program memory of the chip. And this is always, the same location. And it's hardwired in the actual building of the hardware, the logic gates and the transistors and so on, that, for example, when you power on, you jump here. When you get a high priority interrupt, you jump there, and so on.
So you were saying that they interrupts generate a call statement?
Mm-hmm.
Okay, so if that's the case, do we need like a pop at one, like the low priority or high priority functions?
Effectively, but you're going to do a return, but you're going to actually do a ret fee. So when you're done with your interrupt, you're going to do this return from interrupt instruction. And that will do 3 things. It'll enable interrupts, it'll pop the value from the top of the stack, and it'll go to that value that was popped. Does that make sense?
Okay, so that wouldn't go to the next line under, what is that, low priority, so X18?
No, when you get an interrupt, let's say you're in your main program and you're executing this instruction when an interrupt occurs. So here's your main program. Let's say you're executing this instruction when your interrupt occurs. The address of this instruction gets pushed down the stack. You jump to the interrupt code, you execute all of that. Eventually you say ret fee. It pops the stack, which was the address of this instruction, and jumps there. So it'll come back to right after where it was when it was interrupted.
Okay, thank you.
We're going to do this in MPLAB in a minute. So how do interrupts get triggered? So we'll look at that in MPLAB. But for example, if I were to set up int 0 interrupts and then I put a wire on my protoboard between 5 volts and pin 8, right, that would trigger an interrupt. And the CPU will magically jump to location 8 or 18 depending on the priority level. Alright, so ignore the setup for now. The main loop, toggle bit 0 of port A, delay for a while, branch back to main. Delay is the same code that we were using before. What happens when we get a high priority interrupt? We toggle bit 1 of port A, and then we clear that interrupt flag. Okay, intcon 0 has a register called int0if, and we're going to clear that to say disable interrupts. So that'll put a 0 into here, not disable. That'll clear out the interrupt request. If we don't do that, it's going to keep trying to interrupt us. And then we do our ret fee. Low priority interrupt, we're going to toggle bit 2 of port A, and then we're going to clear the int1 interrupt flag, and that's located in intcon 3, and then we'll return from the interrupt. And the rest of this is all set up. Hold on, I'm muting people. All right. So let's look at the setup here. So clear F port A, port B, just put them in a known state. 7F into ADCON 1, always do that. Okay. We're setting up tris A to make those low 3 bits outputs. So we're putting an F8 into tris A. Right? F8 is that binary pattern. So those 3 least significant bits of port A are outputs. Everything else will be an input. Port B is all your ports are set up to be inputs by default. But if we wanted to be precise, right, we could load this bit pattern into tri-state B to make B inputs. But we don't have to do that because they're inputs by default. All right. Bit set file intcon 0 PEIE or intcon PIE. So I'm going to change this because I don't want you to use PEIE. That's peripheral interrupt enable bit. That's meaningless to us. What we really want to do is enable global interrupts at a low priority and global interrupts at a high priority. Okay, so I'm going to say global interrupt enable low. So let's enable low priority interrupts. And down here, when we say bit set F intcon GIE, I'm going to change this to GIEL. And I'm going to say enable high priority interrupts. And I haven't changed the code, I'm just changing how it appears, right? GIE and GIEH are the same thing. PEIE and GIEL are the same thing. They're both a 6. These are both a 7, right? But since I'm enabling priority levels, I'm going to call this global interrupt high and global interrupt low. And I'm actually going to move this one down to the bottom because the last things I want to do are enable my interrupts. Okay, so let's enable int 0 and int 1. So int 1 enable is an intcon 3, so I set that bit. Int 0 enable is an intcon, so I set that bit. So that's these first 2 statements. These interrupts are high priority by default, so I'm going to set interrupt 1 to be low priority by clearing int 1 IP and intcon 3. Okay. Got to ask questions about this if it's not making sense, because this will come back again and again. Intcon 3 has a register int1 IP. The datasheet says if I set that to a 0, it'll be low priority. So I want to clear int1 IP in intcon 3. That's what this statement is doing. Right? Bit clear intcon 3, comma int1 IP. All right. We always want to enable priority levels. So I'm going to move that in the beginning. We're clearing int1 IP because that's how we make int1 low priority. Right? If it's equal to a 1, it'll be high priority. And this picture shows the default value is a 1. So by default, int1's high priority. Same thing with int2. If we wanted int2 to be low priority, we would clear int2 IP and intcon 3. All right, and then we want to clear the interrupt flags because they might have already been set. So we're going to clear int1 IF and int0 IF, and those are in these 2 locations. int1 IF is an intcon 3, int0 IF is an intcon. So we clear those, and then we go ahead and we enable high and low priority interrupts. That's those last 2 BSF instructions. At that point, our whole interrupt system is armed and we're ready to receive interrupts. And anytime an interrupt occurs, we will vector to one of these locations. Okay, I'm going to modify something else in here, because remember, when we use our delay code, we're supposed to load a value into dcount to say how long do we want to wait. Okay, that's the number of tenths of a second. So before I call delay, I'm going to load dcount. Okay, so I'm putting a 10 into dcount, and then I'm going to call delay. Alright, so let's build that, and let's go ahead and simulate it. So let's look at port A. Let's look at the stack pointer. Let's look at the top of the stack. And I'm not going to worry about all of this other stuff. I'm going to put some breakpoints in here, though. So I'm going to put a breakpoint right here before I start my main loop. I'm going to put a breakpoint at location 8. I'm going to put a breakpoint at location 18. Actually, I'll just put a breakpoint in the beginning. I'll clear that one out. Alright, so let's debug this. Your debugs have to go on executable statements. And again, OR is not an executable statement. Alright, so let's go ahead and run this. And let's watch our variables. Is there anything else I want to watch? No, okay, so we're in our main program. We're going to go to our label main. We're going to clear port A and port B. We're going to set up ADCON. We're going to set up tris A. We're going to do a whole bunch of interrupt configuration, and now we're going to go into our main loop. And I'm going to sit here and I'm just going to start looping. And you can see my W register there on the bottom is counting down. Each time it turns red, it's B5. And I'll go through again. It'll go to B4 and B3 and B2. Right? And this is going to run 195 times before it gets down to 0. And then it'll decrement my D count, and I'll go back up, and so on. Now let's say I want to debug this. Let's say I run this code and my LED is not blinking. What can I do? Let's change this. Let's put a 3 into W instead of 195. Because I don't mind stepping through this loop 3 times. And up here, let's put a 2 into decount instead of a 10. And let's run that. So we're testing our code, right? I don't want to step through 195 times 10. That's 1,950 iterations of that loop. So I've just made my loop a lot shorter. So I'll go through my initialization. Okay. Notice port A, the least significant bit is a 1. That's what that bit toggle did 2 statements earlier. And now I'm going to get ready to call my delay. So here's my inner delay. W is 3, W is 2, W is 1, W is 0. I come out of that and I decrement my D count. And I can add that variable if I know where dcount is. Right, dcount is 2, so I'm going to decrement that to a 1. And I go back to my delay. I move a 3 into W, count down to 2, 1, count down to 0, come out of that. Decrement delay. Decrement decount, it's 0, so I'm going to return. I just return from my call to delay. And now I come back up here and I bit toggle port A, and you can see that bit changed to a 0. Okay, so that might be what I was doing if I was having trouble with my delay loop itself. So let me get rid of these. And let's go back to our full-blown delay. So I'm stepping through here. And I'm in the middle of a delay loop. Alright, let's fire an interrupt. So I'm going to set up some stimulus. So I'm going to do RB0. And I'm going to give myself the option of making it high or low. Alright, so I'm stepping my code. I'm definitely in this loop, right? Let's set RB0 to be high. Okay, so it tells me RB0 fired, so that's high. Let's step one more instruction. I'm supposed to do this branch if not 0. I'm supposed to do a decrement. Guess what just happened? Everything just changed. Okay, my program counter, which I can see up here, is 8. And I'm blinking down here on this line. This is line 8. I have vectored to my interrupt code. My stack pointer changed to a 2. And my top of stack is set to 4C. 4C was the address of the instruction down here in this delay loop. Okay, I've just jumped to an interrupt handler. And this code says let's go ahead and jump to H-prio. So I'll step that, I come to H-prio. I'm going to toggle another bit in port A. You can see port A is equal to 2 now. Okay, bit 1 has been turned on. And now I'm going to clear the interrupt flag. And I'm going to do a ret fee. What's going to happen when I say ret fee? It's going to pop off the top of the stack, right, which is a 4C. So it's going to decrement the stack pointer to 1. And what's my program counter? 4C. Right, I just returned to where I was when I was interrupted. And now I keep executing. And if I fire RB0 to be high, it's not going to do anything because RB0 is already high. And it's not the level of RB0 that causes the interrupt, it's the change. It's edge triggered. So I have to force RB0 low, which still won't generate an interrupt because I said positive edge. And then let's fire RB0 again. And now we vectored back to location 8. Alright, I can fire, let's make that low again. So let's fire RB1. Let's do a low priority interrupt. So we'll step, bingo, we jump to location 18. So we're in the middle of a low priority interrupt routine. Top of the stack is 4A, that's where we were when we were interrupted, so it's remembering that. And low priority interrupts are automatically disabled because we just got a low priority interrupt. But let's also trigger a high priority interrupt. So we're down here at location 18, we're about to go to El Prio. We start executing our low priority routine, which says toggle bit 2 of port A. So that changes to a 3, but guess what? It just noticed we have a high priority interrupt and it jumped to location 8. And we now have another thing on the stack. Our stack pointer increased and it saved that 5E. That was the address of our interrupt handler. So we go to our high priority code. And at this point, high priority interrupts are disabled. So if I set this low and high and low and high and low and high, nothing's going to change. Right? So it toggles bit 1 of port A. So port A goes back to a 1 and a 0. And then it clears the interrupt flag and then it does a ret fee. Where is it going to go when it returns from the interrupt? It's not going to go back to our main program. It's going to go back to where it was when it was interrupted, which was in our low priority routine. It's going to go to location 5E. So when we do the ret fee, we end up down here, program counters 5E. And we're back in our low priority routine. And you can see over there on that right, int1 if is 1. That's the flag that says I'm requesting an interrupt. It's about to clear that. So we clear that bit. And now you can see it's a 0 there on the right. And then we do a ret fee. Where's the ret fee going to go? It's going to go to location 4A. Okay, it's going to take us back to where we were in our delay loop. So we execute that. And now it popped that off the stack, and our stack pointer is back to 1. Why is our stack not empty? We've been saying stack pointer should be 0 when the stack is empty. We came back from the interrupt. Why is the stack pointer not 0?
Is it the beginning of the go-to, right?
Almost. It's the call.
Call.
Right, so we made a call to delay. We're treating this as a subroutine. So this top of the stack, 46, is presumably the address of this main loop. So let me cheat. Let me decrement my D count to be 1. And let's continue going through our inter delay. So we decremented W to a 0. We said branch if not 0. So we fell through the branch. We're going to decrement D count, which is currently 1. We decrement that to a 0. You can see it in red. If it's not 0, we're going to go back to delay. So we don't do that branch. And so we do the return from call. So when we return, we should go back to location 46. That'll empty out the stack. Stack pointer will be 0. The stack is empty, and our program counter is 46. And we're back from this call. So everything is nested inside everything else, right? We have all these calls and returns. We're making jumps from one function to another. And in the middle of all of that, if you get an interrupt, you can suddenly find yourself at location 8 or 18. Do what you got to do, come back from the interrupt. All right, so that's an example of stepping through this and seeing what the interrupts do, and so on. And let's throw this into the simulator. So that was lab 4. Alright, so my simulator runs at half speed, so I'm blinking every 2 seconds, right? And I'm in this very tight loop, right? I'm just going from 4A, 4C, 4E, and just, back and forth between those 3 instructions. And there's nothing in that code that says if RB0 is 1, then do this other thing. But as soon as I fire RB0, it immediately toggles bit 1. And as soon as I fire RB1, it immediately toggles bit 2. Right? This is the essence of interrupt-driven code. I have a main program that's always doing the same thing, but I can get other behavior to occur immediately in response to some outside event. So this is a little freaky the first times that you play with it, but once you play with it enough, you start to recognize what the intended behavior is, right? And this is how operating systems work. This is how, devices like cell phones and stuff work. This is how keyboards work. This is how everything works. It's all interrupt-driven, right? If you had to write this program to continually check these 2 bits and then do something if that happened, it would be a really complex program. If you had to check 1,000 different things, it wouldn't be tractable. So it's all done with interrupts. Alright, so let's look at the actual experiment you're going to do for Lab 4. It's a single experiment. And you can use this code as sort of a piece of it, right, and modify it. So your main program toggles bit 7 of port B every 10 seconds. Okay, so every 10 seconds turn it high, 10 seconds later turn it low. So play around with the timers, figure out how to make that happen. And then while that's happening, anytime you get an int 0, toggle RB6. Anytime you get an int 1, which should be set to high priority, toggle RB5. And anytime you get int 2, toggle RB4. Your test plan is expected to test when one of the interrupts occurs only and when multiple interrupts occur simultaneously, like we did in the simulation a few minutes ago. So make sure that you have screenshots showing RB7 is high and then showing RB7 is low. Okay, and then fire RB6 and show a screenshot where fire int 0, show a screenshot where RB6 is toggled. And then fire int 0 again, RB6 should toggle again. Do that for int 1, do that for int 2 also. And then do the extra special case where you fire int 2, show a screenshot as you're single stepping of processing the int 2 code, but before the int 2 code finishes, fire either int 1 or int 0, a high priority event. And show a screenshot that you were into that code, show the resulting change to either RB6 or RB5, and then show a screenshot where you go back to finishing your int 2 handler, and then RB4 changes, and then you're back into your main program. Okay? Basically, you want to use the simulator to convince yourself exactly what's happening here, and that is exactly correct. And then you want to document that. That's what the whole lab report is about, is documenting what you're observing. So whatever screenshots will help with that, whatever variables you want to look at will help with that, right? Put all of that into your report. And so yeah, good question from someone. This setup code, this is not always the same. Okay? Good chance that, let me go back to the slightly different version. Good chance you're always going to want to set IPAN and RCON. You're always going to end by setting global interrupt enables low and high, right? But these really depend on which interrupts you want. If you want int 0, you have to set int 0 IE. If you want int 2, you have to set int 2 IE. If you don't want int 1, don't set int 1 IE. If you want these to be high or low priority, you either set or clear the corresponding bits. And then generally, whatever interrupts you're enabling, you're going to clear their interrupt flags before you go ahead and enable global interrupts. So a lot of this is the same, and the essence of this will always be the same, but the details will definitely change from one run to another. Let me show you just one more thing in here. Suppose we don't clear this interrupt flag. So let's go ahead and run this. So we're stepping through our delay loop, and I'm going to go ahead and fire RB0. And after 1 to 2 instructions, we're going to vector to location 8. Okay, location 8, we're going to toggle bit 1 of port A, so you can see port A just turned to 3. And we're going to do a retfee. Well, we didn't return to our delay loop, we seem to have gone back to location 8. And we execute our high priority code and we retfee and we come back to location 8. Right? Why is this happening? Because intcon has this int0if flag, right, that second bit from the right, which is still a 1. That's what's requesting the interrupt. That's the thing going into the AND gate in that picture from the data sheet. Right? Unless I clear that bit using this BCF instruction that I commented out, it thinks there's still an interrupt request. So it's important to clear these. And so your interrupt handling codes will usually look like do some stuff that you want to do and then clear the interrupt request and then return from the interrupt. But the stuff you want to do is totally up to you. Alright, so question, what's the difference between intcon and intcon3? They are completely unrelated to each other. So intcon is used to enable or disable high and low priority interrupts, to enable interrupts from timers, int0 and port B, and it stores the interrupt request flags from those 3 sources. Intcon3 sets priority levels for int1 and 2, enables int1 and 2, and saves the interrupt flags for int1 and 2. Intcon2 is used to control the edge for int0 through 2, whether interrupts on the rising or falling edge. The priority level for timer 0 and the port B changes, and also something called active pull-ups on port B, which is not really interrupt related, right? Totally different registers. PIR lets us contains the interrupt request flags for the A to D converter, the serial transmit and receive, the timer 2 and timer 1, and so on. PIR2 has the interrupt flag for the oscillator and for timer 3 and for the low voltage detection. PIE has the interrupt enable flags for the A to D and the sender and receiver and timer 1 and timer 2. PIE2 has the enable flags for the oscillator and the low voltage detector and timer 3. IPR has the interrupt priority levels for the A to D converter, the transmit and receive, timer 2, right? So it's all over the place. There's no rhyme or reason to any of this. If you're using A to D conversion and you want it to be interrupt driven and you want it to be low priority, you got to hunt through here and figure out, oh, it's bit 6 in the IPR register, and since I want it to be high priority, I should set that to a 1. And if you actually look in the data sheets, when you find any of these subsystems like the A to D subsystem, it will show you in that chapter all the information you need. For example, I'm in the A to D chapter, which is chapter 17, and if I go down here past all of this stuff, I'll see a list of all the registers I might be interested in. There's PIR1, PIE1, IPR1, and so on and so forth. And you know, most of these bits I don't care about, but I care about the AD interrupt flag, the AD interrupt enable, and the AD interrupt priority. Alright, so that's your lab. go ahead and jump into that. I think I've had like maybe 2 people total who've been taking advantage of lab time as far as talking to me and sharing their screen and so on and so forth. I think that's been useful for people, but you know, I'm mostly sitting here playing violin waiting for the Zoom to bing. So if you want to hop into the simulator, definitely do that, and you know, Zoom me, and I can help you with questions or see what you're doing and so on and so forth. Yeah.
I've been having a bit of trouble contacting you during lab hours.
Well,
I managed to do everything on my own, but...
So if you go to Zoom, so I'm in my office hours instead of class, right? So if you go to Zoom and you connect to that meeting, it'll put you in the waiting room, okay? And if you're not coming in to me right away, it means I'm helping somebody else. And if there's 3 people queued up already, then after I help all of them, you'll come in.
There was a time when I went into, after a lecture, I went into the Zoom room again, and it was good 15 minutes before I gave up.
Yeah, I mean, I can get a queue of you know, 20, 30 minutes, and I'm also getting students coming in for advising. But I will not just leave at 4 o'clock, okay? I will stay there as long as there are people in the waiting room today, and on Thursdays I'll at least send a note and let people know, you know, how many people are in front of you, if it's getting close. But today I will definitely be there, right, as long as people are there, at least until 3:50. And if there's still people in the waiting room, I'll stay on and I'll get through everybody. So just go ahead and connect to Zoom and turn on the sound or something, so that you know when your turn comes up. Does that make sense?
Yeah.
Okay, cool. All right, go ahead, work on your lab. I'll switch over to my office. I will catch you later. Otherwise, I will see you on Thursday, 12 o'clock midterm. Thanks.